Hello, 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 hello. Root Beer here with the very last question on the 2015 MMC Manitoba Math Contest. That's right, it's question 10. Our patience has paid off and we are there. We just have one more question to go and we can taste freedom. It's been a good contest so far, I think. So let's take a look at question number 10 and what it's got in store for us. The expression n factorial denotes the product 1 times 2 times 3 all the way up to n. So this is something that you should know, but it's not gone over everywhere by the time you hit grade 12. So it's nice that they remind us. So it's read as n factorial. For example, 5 factorial is 1 times 2 times 3 times 4 times 5, 120. 6 factorial would be this multiplied by 6, so 720. 4 factorial is 24, 3 factorial is 6. These factorials are numbers that, frankly, if you're writing a grade 12 contest, I recommend that you know. Know your factorials up to something like 10 factorial, although I admit I only know it up to about 8 factorial. But they're useful numbers. They do pop up from time to time, so they are something I recommend you know. If you didn't, there's a nice definition. So we've got our definition. We move on. We've got two parts in 10 here. So part A and part B, which is a bit of a departure, frankly, for question 10 on these contests. Usually it's just one thing. Usually the A and B stuff is earlier in the contest. Anyway, A, the product 2 factorial, 3 factorial, 4 factorial times 5 factorial, 6, all the way up to 12 factorial, can be written in the form m squared times n factorial, where m and n are positive integers. Find a suitable value for n and justify your answer. Okay. Alright. Squared and then an n factorial. All the way up to 12 factorial, that's going to be a bit of a pain. So while I think I could do it, I don't see an obvious... Is that an obvious avenue for attack? I think there's one formulating in the back of my head. But when I'm stuck like this, on sort of a question like this, it's written, it's a question that's got multiple parts. The parts should connect. This happens a lot on, say, Waterloo's Euclid contest. When I'm stuck with a part and I don't know how to do it, I look for later parts for guidance, because the mark of a good contest, and the Waterloo contests do it, the Manitoba contests I've noticed do it, the mark of a good contest is if you split up into parts, at least for the harder questions, they tend to flow into one another. So in part A, you'll make some observations that'll help you understand the pattern you need in part B, that'll understand the generalization you need to prove in part C, the yada yada yada. So if I'm stuck on, say, B part, on question 9 on a Euclid, I will look to its C part and say, okay, here's the big thing they're looking at. Does that give me some direction for my B part? And usually it will, not always, because they're not so obviously connected all the time, but usually. Okay? So I'm going to look at the B part here and see, does that guide me in any particular manner? So, B part, prove that for every n, so it's the same sort of thing, a product all the way up to a multiple of 4 factorial, can be written as the product of a square and a factorial, which is what they're talking about here. So, does this help me for part A? Not entirely, although it does tell me why the 12 is here. And it does suggest to me that maybe I can solve both of these by looking at the smaller ones, like n is 1, or n is 2, going up to 4 factorial and 8 factorial respectively, and seeing, can I notice something there? Because if I can solve B, then I've solved A. Now, this isn't always what you want to do. Okay, some of you out there might be able to do A but not B. So, by all means, write down your A. But if you notice that A part can be solved by doing B part, because B part is more general, then make a note of that. Say, oh, if I solve B, I can solve A by yada yada yada, and it follows from whatever, whatever. And then you can cut down your work by just trying to solve B. I'm going to go for B, and I think we'll get A as a nice little result. So what I'm going to do is I'm going to investigate. I don't know how to break it up in a nice logical way into a square and a factorial, but B part has given me the suggestion that maybe look at 2 factorial times 3 factorial times 4 factorial, and that's what we're going to do. So first I'm going to explain why I can do this, why I don't have to actually do b. Notice that a follows from b. Now I admit in a they are asking for a specific n. They are asking for n factorial. And so we will at the end have to work that out. So notice that a follows from b with little n equal to 3. We will work out the capital N that they asked for A after proving B. Okay? So I don't know how to prove B yet, but let's investigate. For n equals 1, we're looking at 2 factorial, and this is bugging me, so I'm going to put a 1 factorial here. Because 1 factorial is just 1, and it doesn't matter. Okay? So when I worked that out, so you don't have calculators, but you do get 1 times 2 times 6 times 24. This is why knowing some of the smaller factorials is helpful. 1 times 2 is 2. 6 times 24 is some 144. Oh, which is 2 factorial times 12 squared, although I don't know is this the only way to do it? I'm not sure. Okay. Now for 2, we get 1 factorial. And again, I'm putting the 1 factorial in because I want all the numbers to work with. Okay. And there has to be some reason why we're doing multiples of 4, although I'm not entirely sure what it is yet. Now this one, well, I do know what all these factorials are. I don't think it'll serve me in any way to actually calculate what this number is. So what are we left with? We're left with the fact that they're factorials. Okay, so I'm going to write them out, and I'm going to write them out in maybe an unexpected sort of way, but I'm going to try and pair up, because we need to get that square. Right? We need to get a factorial, and I imagine the factorial is what's going to be left over. We need the square. So what I want to do is, for example, this 1 factorial times 2 factorial times 2, he's got a factor of 7 in it. I know he definitely has a factor of 7. It has to come from the 7 factorial. He has another 7 coming from 8 factorial. And so maybe I can sort of pair these up in a meaningful way. So I'm going to try and write out this and its factors in a way that makes sense and allows me to sort of easily visualize and pair some things up. Okay? So this is 1 factorial times 2 factorial, which is 1 times 2, times 3 factorial, which is 1 times 2 times 3. So I'm making sort of a triangle here of all the factors. Okay. But then what can we do? Well, we can... so these 7s, they would go together to make part of a square. So that accounts for 7 squared. As a matter of fact, I think we just take all the possible pairs and we'll be left with some numbers left over. So that's 7 factorial squared. This guy here is 5 factorial squared. And this one here is 3 factorial squared. And here we've got 1 factorial squared, which doesn't really need to be added because that's 1 squared, which is 1. And then what's left over? We have 2 times 4 times 6 times 8. So while when multiplying all these together we get a square, we don't get a factorial over here. But it's very close to a factorial. He's like 1 times 2 times. He's got the same sort of progression, but he's got extra factors of 2. How many extra factors of 2? 2 to the 4, which is just 4 squared. Or 2 to the 2 squared. I think I'd rather write it as 2 to the 2 all squared. So this is 7 factorial times 5 factorial times 3 factorial times 1 factorial times 2 to the 2, which is n, squared, times 2n factorial, right? 4 factorial. So I think this pattern will generalize. Let's try n equals 3, which will actually be the A case. So we'll have solved the A case as is. So for n equals 3, we'll get 1, 1, 2, 1, 2, 3. It's going to be boring for a little while because I'm just writing these out. But I think we've got it. Let's just see, does all this generalize? So products of the odd factorials times 2 to the n, and that gives us the square. And then we have 2n factorial. I think that's our pattern. I should have checked, does that work for the one that we already worked out, the 12 and the 2 factorial, or the 2 factorial. Should have checked that out before this, because if I'm off, or if I'm wrong, then I will have wasted a bit of time making this triangle up. Time that could have been better spent working out the actual answer. But I'm confident in what we've seen so far. So that's 11 factorial squared, and then we get 9 factorial squared, and then we get 7 factorial squared, and then we get 5 factorial squared, and 3 factorial squared, and 1 factorial squared. We're left with 2, 4, 6, 8, 10, 12, which is just 1, 2, 3, 4, 5, 6. 6 factorial. We've taken out 2 to the 6, which is 2 cubed squared powers of 2. Okay. So now we need to sort of write this up for 6, and we can also make the observation that for A, m will be 2 to the 3 times 11 factorial, 7 factorial, or 9 factorial, 7 factorial, 5 factorial, 3 factorial, 1 factorial. And n will be 2 times 3, which is 6. So we have figured out A. There it is, and we've justified it. Okay. So for B part, we do need to prove this. We've got the pattern. Now it's up to us to explain how do we know this is always going to work. How does this always work out? Okay. So we group it in pairs. So for any n, 1 factorial times 2 factorial times all the way up to 4n factorial. Can be rewritten as 1 factorial, 2 factorial, 3 factorial, 4 factorial, 4n minus 1, all the way up to 4n minus 1 factorial, 4n factorial. Okay. And now we're going to take out that factor. So we'll get, so this is really 2 times 1 factorial, 1 factorial. 4 times 3 factorial, 3 factorial. 4n minus 1 factorial, 4n minus 1 factorial. And you could justify this by, like, how can we pop out these numbers? Why does the 4 come out? Since k factorial is just k times k minus 1 factorial. Okay, that's a nice recursive definition there. It's very useful. And it's something that if you didn't know, you should note that for the future. Okay, so which we can further rewrite as we'll take out 2, and it's 1 factorial squared. 4, 3 factorial squared. 4n minus 1 factorial squared. Okay. Which is 2 times 4 times 6 times yada 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 all the way up to 4n times 1 factorial, 3 factorial, all the way up to 4n minus 1 factorial squared. And then we take out a factor of 2. I want to make this a little clearer. So 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 2n. And then we keep our square. But I'm going to say there are 2 to the 2n. So there are 2n many 2's. So I'll just make that observation. So now I can say this is 2 to the 2n. 1 times 2 times 3 all the way up to 2n. 1 factorial, 3 factorial, all the way up to 4n minus 1 factorial squared. And then this guy becomes 2n factorial, and this becomes 2 to the n squared. And then you can write it one final time, grouping the two as a square together, but instead we could just say it's m squared, or n factorial, where m is 2 to the n, 1 factorial times 3 factorial, all the way up to 4n minus 1 factorial, and n is 2n. Okay. We've shown our rough work, although you don't need to do that stuff with the green boxes showing how you get these things. Maybe if you wanted to just show A, yeah, show the green boxes. But for B, what do we need to do? We need to change that expression into one that is a square times a factorial. Well, we've done that. We don't have to say, aha, this is where we got our inspiration. We just need to show, rewrite it like this, then this, bring these out, group this as a square, yada, 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 and then get your answer. Okay, you don't have to justify your inspiration, which I see a lot of people try and do. I see people get caught up. It's very hard to justify your moment of inspiration. All you can really do is say, here's an example I worked out, here's an example I worked out, here's an example I worked out. Can't you see the pattern? I saw the pattern, that's what it is, and that's how we got the end. Don't bother with that. The math is there and correct. We don't have to explain how did we know to write it as a triangle, write the factors as a triangle? We didn't. I just decided to line them up that way. I decided to line that up way because the 7s caught my eye, and that's not really anything that you need in a math proof. Okay? So brevity is an important thing to practice, as well as logical flow and consistency and putting everything in there that needs to be there. Okay? There is such a thing as adding too much information. We have our rewrites, we have our explanations. That's good enough, and we did take the time to say, for A, when little n is equal to 3, this is what the capital N would be. And I think that's the one we were asked for in A. Yeah. Find a suitable value of n and justify your answer. Well, we did that. Okay, we did. It was on the preceding page, wasn't it? Yep, 6. Okay, and that works out just fine. Didn't need a calculator. I thought we might have, but no, the numbers got too big too fast. Although with 12 factorial, how useful would a calculator really be? So that does it. That's the 2015. It's been a great contest. I certainly liked this. Really liked this last question, actually. Hopefully you guys liked this. If you're planning to write the upcoming Manitoba contest, good luck with that. If you like the video, if you like the contest, feel free to show that by liking, subscribing, whatever you want to do. No matter what, I will see you guys for more math contests in future videos. So thank you guys for watching, and have a wonderful day.